Alright, here I've started Ugene, so let me just review very quickly how to use it. I'm going to go over to File, and I'm going to go Open, and it may or may not ask you to start a project. You don't have to start a project. I mean, you could start a project and just keep all your files organized if you want to learn how to do that. But you don't have to do any kind of project. So we open it up, and there are data samples and things that it comes with if you want to like explore that and learn to do some other things. But I'm going to instead go to my own files, and we'll find some things here to look at, like Homo sapiens GPX2 and 3. So let's open these two. Now I use the Control key on the keyboard, and I'm going to choose two GPX files, and I'm going to open them. So I went and found my files, and these are two separate FASTAs. You could just as easily put the two FASTAs in one FASTA file, the two sequences in one FASTA file, and open the one, but I had two separate ones, GPX2 and GPX3. So I'm going to open those. All right, and I'm going to open them in separate sequence mode, but realize I could merge those two. It gives you all kinds of interesting things you can do with this. You could create an alignment here if you wanted. We're going to do an alignment, but I'm going to keep them as separate sequences so that you can see how to manage them. So I have the first one here, GPX3 and GPX2. I think we're on GPX2 here. You can see 584 104. I'm trying to find the exact numbers here. Yeah. Okay, this is 2. I mean, that's 3, and this is 2. All right, and you can go back and forth between these two. They're also up here. You can do them like this. It's not, actually, I think I like it better when I just do it across full screen. But I can go back up here a tab. I can go to, this one is 2, and this one is 3. I can see them. I can scroll through them. Essentially, I'm, as you can see here. Now, what isn't, let's see, let's pull this down a little. Alright, so I can scroll left and right. Actually, you do it up and down here. And you can see the whole sequence this way. Now, notice as I do this, there's a tab up here that is showing where you are in the entire sequence. So as I move this, the little square up here moves with me. And this tells me where I'm at. 1615, 1615 bases into the sequence. The entire thing looks like it's about 4,888. No, 4,901 is the maximum size here. So you can go through and you can actually look at it. Now these are both strands. Now you can change this view. I can look at just this. Let's see. I can make it multi-layer, or I can look at several lines at once or just one. I can make it single-stranded again. Let's see. I can show all frames. It's here we have it under Do Not Translate. I can translate, and I can show all 3 reading frames. This can be useful to you. Now, here we're only one strand. You can even make it double-stranded, and it will show. Let me show that. All right, so here's your regular strand, and here is the amino acids that you would be creating if you were to translate it. And you can see you can do both the complement and the original strand above and below. You just got to keep track of which one is which. If you don't like both strands, you can go back to one. Here we go. And so these are the amino acids that would be created by this this piece of DNA or RNA. So you do have to keep track of if you're an RNA or DNA. If it's DNA, remember you need to translate it into an mRNA and then do this. But if you don't do that, look at the complement. The complement is the RNA translation. So this is useful for you if you're trying to translate your DNA. This essentially to an amino acid sequence. This will do it for you, and you can look through. Now, of course, these start with methionine. So if we're looking at it, we might see here methionine. Maybe this is in this middle reading frame. All right, and we would start here, ATG, and that T goes up to the M, so that's methionine. And then you would, but we're at the end of the sequence, so that is unlikely to be the starting methionine. If this is an mRNA, then the first methionine should be the start codon, and that would be here. So it's very likely that if this were an RNA, then we would start here and start reading until we come to a stop codon, and that would be here. This is unlikely. This is probably just intervening sequence here, since this is just a piece of chromosome 4. It actually says it's GPX, but I don't think that's actually the start codon. But the idea here is just to be able to see this and get used to using this, because we will use it. I'll give you assignments that you will need to use Ugene. Now the thing I really want to show you is that there is a better dot plot program on this one, and dot plot is probably your number one useful tool. So I'm going to go build dot plot, and we have to load the first sequence. Well, we were using the 2 FASTAs we were like, so let's go find those again. GPX2. All right, so that went in here, and then we go GPX3. Find it. There we go, and we're going to compare those. And we're not going to compare against itself. You could put in just one and click compare against itself, and you would be done, and it would compare it against itself. We're going to go next. All right, now here is the part where you need to learn some specifics to tune in, like we did the thresholds and the window size for everything for the other one. We have to do this for this one as well. So we can search for direct repeats. That's the standard concept. But you can also search for inverted repeats. This is actually useful for finding things like termination sequences, and we'll talk a little bit about that later. But you would click on this if you're trying to find those hairpin loops that I put a video out on. So we're not going to do that today, but you would. Now here is the repeat length or identity. What we're looking for is how big of a window are we going to look at to make dots. In other words, do we look at window sizes, and depending on your sequences you have to adjust this. Now they'll have a recommended, and they recommend with this size doing 7 base pairs at a time. Now this would mean that to get a dot you would look at 7 bases at a time, and you would have to have all 7 of them be identical to get a dot. Let's reduce that. Now you realize this is going to be, if there are 7, percentage-wise, you would go by 7 over 100 percentage points for it to make a difference in the thing. In other words, 1 out of 7 is different. How many percentage? In other words, what is 6/7 or what is 5/7? 7/7 is 100%. So 6/7 would let you have 1 mismatch, or you have to get below 6/7. So let me think. What is 6? Let's just make it easy. Let's make it 65%. So 65% of 7 is probably about 4, maybe 5 that have to be the same. So I'm just going to put that in there. And then this is probably going to be way too messy, and it's not going to give us any information, but we'll play with it and see what we can find here. So I'm going to do this. All right, and here, yeah, it's way too messy. It's almost black. It's almost solid here. So let's scroll this down. Come on. This is the dot plot, and as you can see, this should be moving. Don't know why. I'm just going to delete the whole thing there. Oh, it got rid of everything. Here we go. We'll scroll down. No? I wanted to get rid of the sequence, not the dot plots, and the sequence is what went away. Well, I'm going to do away with all the sequences here. Alright, and we're just going to have the start page, and I'm going to do the dot plot over. So build dot plot, scroll down, okay, then we go, the recommended is 7, and we decided on 65%. Okay, but I still can't get the, I want to get rid of this. Stretch it, and this normally works. Huh, really strange. I don't know why it's not working, but I wanted this to be stretched out to be a longer plot. We'll work with it as it is here. I don't know why this isn't. And when I tried to kill this before, it killed everything. So, but as you can see, when I do this, it does give you where you're looking at down here. So I created this little square, and that's showing you this is where in the sequence that you were looking. So that could be useful to you if you're looking for something. But of course, this is not useful. There's too much. It's finding too many dots. So we go back up here and we click on the actual thing, or right click, dot plot, and we are going to filter, we're going to change the parameters, and that'll bring this back up. And so what we're going to do is we're going to go back from 65%. We're going to go to, let's go 80%, and we'll see how this changes. Okay, well, it's better, but it's not perfect. We need less than this. This is way too much. Still way too busy. So we go parameters, and so, well, let's just make it 100% and see what happens. Well, this is interesting. Okay, so we have more now. They're little dots, but no consistency here in GPX2 and GPX3. We just don't see any consistent lines that we would expect to find homology. Are GPX2 and GPX3 not related? Well, according to this, it wouldn't be. But we need to keep altering our parameters. Let's go and let's increase this. And I'm going to go to about 32. And I'm going to reduce this to about 90. And let's see what we get. Now we get nothing. That's too stringent. There's nothing to see. So we go in parameters, and we're going to cut this back to 20. Still nothing. Oops, hit the wrong one. Alright, let's go to 17. Still nothing. Alright. But we know when we get too low, it's too messy. So let's go to 12. We're beginning to see little pieces here. You can see small dots around, so we're getting closer. So why don't we, since we're seeing some little dots now, why don't we reduce this a little, and let's go to 80%. More dots. So we're getting better. And then we want those little dots to get a little larger, so let's go 70%. And now we are at a little too much again. So let's go back. Alright, parameters. And let's raise this a little. go to 15 and see what we get. Okay. And so you go back and forth between these two, and eventually you can find probably what you're looking for. It just takes a while to kind of tune in. Now here we're getting to something that might be useful. I'm really upset that I can't reduce this size. I don't know what's going on this this version of Ugene. Usually I can just go here and just stretch this right down and make it drop out of the way. Can I do that down here? No, can't do it here either. I'll switch to a different computer. But as you can see, this one is not showing much what we call homology. In other words, we want this diagonal going across from here down to here. At least in this version of dot plot, it would be from here to here. And you're just not getting it. It would be right across the page, and you're not seeing that. These two just apparently have diverged quite a bit, and it's very difficult to actually get them to line up. You should be able to get something if you continue to work at it. I'm going to go down here, and I'm going to go up here and see what we get. And so we've reduced it back down to very little again. Let's try a couple more. A lot of times you can do something. Let's go way up. Let's go 32 again, and go way down here. Okay. Still just nothing huge here. I get something that looks kind of interesting going this direction, but nothing there. Now one other thing we can do, let's go back, alter the parameters. Alright, and I'm going to search for inverted repeats as well. And we're going to see if things maybe have been pulled out and put in backwards. Essentially, small segments have been cut and then they've been reinserted in the opposite direction. Let's see if we see those. There we go. So what is this telling us? Well, actually what this tells us is something that that I should warn you about. Is what we have here is we were comparing a DNA, and this says it's DNA on this particular chromosome. Let's see, do we have the, and then this one is the other one. Alright, what we have is they've sequenced these genes in opposite directions, and one is going one direction and one is going the other. They actually were quite similar, but we have opposite directions going on. In other words, one is the complement and the other one is the coding sequence. And they get this wrong and they label it wrong commonly. So this is a good example of, you need to play with it, and if you're not getting what you want, you may have the wrong sequence. In this particular case, I kind of knew that this was the case here, and there's really no way in the description to know that they did that. The only way I found that out was to use this inverted sequence, this inverted piece. This is usually used to find terminal repeats, but I would suggest that whenever you're using these sequencing and comparing them, always either click the inverted repeats or find the reverse complement. Actually, there's a place in Ugene that will just convert it for you and make a new sequence going in the opposite direction on the other. In other words, create the opposite strand of the DNA and let you work with that strand. But be aware of this. This is something that's common. It's easy for students to get it mixed up. And you would imagine that, especially when the databases and the labeling gets mixed up, and it happens way too often. So keep this in mind. Here we have it, and so yes, it's actually very stringent, right through the middle here that it stayed. Now one sequence is longer than the other. You get a full sequence, and the other one has extra pieces. That's what this is showing. This is showing that this long one here is pretty close to this middle one, and that. Now here there's some duplications, some little pieces out here. Let's go and do a few more things here so you can get used to. This just is not. There we go. We're going to have to leave this on, but now that we know what's going on, let's go back and do their recommended 7, and let's do what we were going to do before, 65%. Let's see what you get. It should be like totally black on there, though. Yeah. So that isn't good. You always know that isn't. And then let's jump back up to 100% and see what it would have been. All right. Oop, there we go. And that is showing that, yes, these are very similar. Now, if I tried 100%, how different are these two sequences? So if I go just one by one at 100%, they're pretty darn. It is pretty close. Huh? Calculating. All right. There are pieces in here that are missing, but there aren't much. So GPX 2 and 3 look to be very similar, according to this. Assuming that I have the right sequences and they're labeled correctly. But the idea here is they're very similar there. These two. One is simply just longer than the other. All right. This is just an example here. Go and learn to use dot plot on Ugene. It'll be very useful to you. Keep in mind about the inverted repeats. Kind of a warning that do it once with it and do it once without it. All right, nothing when you do it without it. So just keep in mind that just throw it in there. If you're not getting anything, try the inverted repeats and see if that doesn't help you, or go and convert them to the complement and see if maybe it's going in the other direction. They got the RNA and DNA mixed up. I find that that's actually pretty common in the databases. All right, well, it's a shame that there's nobody to check these things. Let's see, anything else? I think that's it for the dot plot. The other thing we need to do is the alignments. So let me very quickly go through here and do multiple alignment. Now we have 1, 2, 3, 4. We have 6 different programs to use. I personally have found if you're going to convert to proteins at some point and you're not going to stick to DNA, that the K-align works the best for if you're in nucleic acids, and eventually though you're going to want to be talking about the protein, that you should probably start with this one. So with an alignment though, you have to give it those FASTAs that have multiple sequences in it. So the input file needs to be a FASTA with multiple sequences in them. So it's a multi-sequence FASTA. And let's see if I have one of those already made. Oh, I know there's one on the desktop because you guys, it was somebody's homework. Let's see here. Here we go. It's in... Let's see, somebody's name, I forget who. So we can find this. Lots of FASTAs here. Let's do it that way. I want only FASTA files. Oh, I saw it, Curtis. Curtis. Yes, right there. All right, so let's open Curtis's and let's align this. We can set the penalties and all of that. Leave it as is. I explained penalties and how to determine what, different changes are. And you can adjust that here if you wanted to. Now we need to give this an output name. Now an output file, we need to decide where we're going to put it. We will put it in, yeah, we'll put it in there. And it needs to be a line, and that'll make it that. And so we're going to call this just my alignment, my align. How about that? And save it there. So it'll be my align, and it'll be in the same folder that's on my desktop there. All right, so we align them. All right, now this may take a while, it may not. Let's see, we're down here, we're at 74%. If you can see down here in the bottom corner, and it says it's running K-align. And there we go, this is the alignment. This is what it says is the best alignment. These are not always accurate at all with a longer sequence. You're probably 30 or 40 is as far as you can go and believe it. You know, this one, I don't know if I would believe this or not. They really aren't. These programs really aren't very good. Dot plot is your best bet to find something. But here's how it would alignment. It looks like there are pieces that align pretty well with these in these regions. This top one doesn't seem to be aligning well. One of them is obviously much longer than the other, it looks like. Here you have a gap. That's an interesting piece. But this is what this program says is the alignment for these pieces. Tell you the truth, with these, I wouldn't believe this. This is probably not accurate whatsoever. But there are alignments. You should use smaller sequences than however long we have here. Let's see, how far does this actually go? This goes to it's roughly 3,735 for the longest sequence. And that's way too long for these to be accurate to any degree, even though you have multiple sequences for it. Use much smaller, 50 to maybe 100 bases at a time, maybe. But of course, that makes it very difficult. But that's the limit of really good alignments are really hard to find. Dot plot is where you should start and look at 2 at a time, and then kind of find the areas that look to line up on all of them and start there and move out. It's really a shame we don't have better software than this. They claim they align really well, but really you have to do a lot of it by eye, and that's why dot plot is your best bet to start with. All right, and just doing them 2 at a time with a dot plot, and then figuring out what pieces are similar, what areas, and then just picking out those areas and aligning them across multiple sequences. And you could find that area in several of them and put that in here. Just those small pieces that have aligned on the dot plot where you see the lines, you would take those out and put them in here, and that's probably the best way to do this. Now you will find that if you were to do this experiment that I just did here, and you were to do this with each one of these programs, what you will find is each one of them will give you a different answer, and that's just an indicator that you need to do it by hand, and you need to learn to do it by hand. That's the old-fashioned way with dot plots, and not try to. There are people who just publish things with an alignment thinking, oh, well, these things are accurate, right? Oh no, these things are like very, very inaccurate without you doing a lot of work beforehand to get these to align. So use smaller sequences after you've looked at them, compared them with dot plot, and I will probably go through and do that with you, maybe on this one, and that should help you out in figuring out how to actually use these. All right, that's our video for today.